Hello, welcome to another module of this course, Analog Circuits. In this module, we are going to take up the topic of active implementation of filters. So, in the previous module, we saw how passive filters can be implemented. Let us now see how active filters. So, at the beginning, let me mention that active filters are one where the gain of the filter can also be controlled, which we cannot do in passive filters. Now, one of the simplest implementation of an active filter is using a simple non-inverting or inverting op amp. Like, so we have say you have op amp in inverting configuration. So, here what you see, suppose we consider this circuit, then you know that VO upon VI will be given by minus R2 upon CS by R2 plus 1 upon CS, this whole upon R1. So, this comes out to minus R2 upon R1 upon 1 plus R2 CS. Now, this kind of circuit, as you can see, using a simple op amp, it is easy to implement this first order filters. But this simple circuit is not enough to implement a second order circuit. So, for a second order circuit, what do we need? So, for example, a second order low pass filter will be something like this. Okay. So, low pass filter will be something like this, a band pass filter will be something like this, so what you see is that just by replacing or interchanging the positions of the L, C and R, we can get various topologies. So, this is a band pass, okay, and then this one is a high pass. Okay. So, you see elements are the same, just how we place them. If you want to make it consonant, this circuit consonant with the others, instead of putting the ground symbol we can just put it other terminal signal. So, here also there is VI, this is VI. So, the difference between these three second order filters, so these are all second order filters. Okay. The difference is only that how these R's, L and C are placed, fine. So, then let us see, on chip an inductor is very difficult to implement, because inductor has a significant height. So, it sticks up from the board. A simple implementation of an inductor using op amps can be done. So, we can replace an inductor with an op amp based circuit as follows. Now, I am claiming that this is a inductor implementation using op amps. So, first see that these op amps, now in order to prove that this is really an inductor, let us first assume that these op amps are ideal op amps. So, if these are ideal op amps, then there is no current flowing into each op amp. Now, in this first case, what is the current flowing through this arm? The current flowing through this arm is V1 upon R5. So, that must be the current flowing through this arm. Again, the current flowing, the voltage. So, let us see, since V1 is the voltage at this terminal, due to the virtual short, the voltage at this terminal also should be V1. Okay. Then what is the voltage at this point? The voltage at this point is this voltage plus the voltage drop across this capacitor. So, it is V1 plus V1 upon R5 times 1 upon C4S. Okay. Then what is the current through this resistance? The current is, can I say, if I consider the current to be in this direction, then this current will be the voltage difference between these two terminals divided by R3. So, this current I, say I3 is given by minus V1 upon R5 C4 S R3. Okay. This is the voltage difference between these two terminals divided by R3. Then the voltage at this terminal would also be R1. Now, this current is actually flowing in this direction, that is the reason we get a minus sign. If we consider current to be in this direction, then we get a negative sign. Now, proceeding similarly, the what is the voltage at this point? It must be V1, right. Now, since no current flows in this terminal and this terminal, therefore, we can assume that the current flowing through R2 is also I3, and so the voltage at this point plus the voltage drop across R2. So, the voltage at this point is V1 plus I3 times R2, which is equal to V1 minus V1 R2 upon S R5 C4 R3. This is R3, this is C4. Okay. So, that is the voltage at this point. Okay. And finally, what is the current flowing through this R1? Now, since again no current is flowing through this terminal, through this line, therefore, the current flowing through this is through R1 is V1 minus the voltage at this point, which is V1 minus this whole upon R1, which is equal to V1 R2 upon S R5 C4 R3 R1. Okay. So, this is the current that is flowing through R1 and also the current flowing into this network, because no current is flowing through this terminal. Now, what do we see here? The current, that is the current I in. Note that V1 is the voltage at this point. Okay. So, the V1 is also the input voltage and I in is the input current, and that I in is given by V1 R2 upon S R5 C4 R3 R1. So, then V1 upon I in comes out to S R5 C4 R3 R1 upon R2. Okay. This is my input impedance, and since S is in the numerator, so this has the same form as that of a inductor. So, by this circuit that I have mentioned, we have actually implemented an inductor. We have not used a real inductor, but we have this circuit behaves exactly like an inductor. However, please note that these op amps were assumed to be ideal, that is no current is flowing inside these op amps and they have a virtual short between their two terminals, which is not always present for practical op amps. Now, what is the utility of this circuit? The first utility is that since we have implemented a active inductor, so that band pass and high pass circuits, if we go back to them for a moment. So, this was our high pass. Now, these two circuits, we see that one terminal of the inductor is grounded. Grounded means like this. So, these two circuits can be implemented using that active inductor circuit which I mentioned. Okay. For a high pass and band pass filters, this is a band pass and this is a high pass prototype. Sorry, this is a high pass prototype. These two circuits can be implemented using this active inductor. The low pass cannot be implemented because the low pass prototype has a circuit like this. So, this low pass prototype has a circuit like this, and that active inductor we saw, the other terminal always has to be grounded. So, we have implemented an active inductor, but one terminal of that inductor is always grounded. So, it can be used only in shunt. It cannot be used in series like we have here, and that is the reason we cannot implement a LP or low pass prototype using this inductor. Of course, there are many other implementations of low pass prototype. Let us see one of them. Let us once again go back to the pole positions of our low pass and high pass and band pass prototypes. So, a low pass second order low pass filter will have a transfer function like this. With a DC gain So, the poles are at this position, 0 at infinity, this radial distance of the pole from the origin is omega 0, and the horizontal distance from the y axis for both is like this. Okay. Then for the high pass prototype, high frequency or gain at infinity is equal to A2. Now, the pole positions again are like this. Two zeros at the origin, and the pole locations are the same as for a low pass prototype. Okay. And finally, for the band pass prototype, now the reason I am elaborating on these transfer functions is that we will see certain similarities in the transfer functions eventually. For the band pass prototype, So, then for the band pass prototype, the pole locations are the same. A 0 at origin and center frequency gain. So, for the low pass case, we had the gain at 0 or DC. For the HF case, we had the gain at infinity or high frequency gain, and for the band pass filter, we have a center frequency gain of this one. Now, the first thing that I want you to appreciate is that, so this is a second order, is that if you see the transfer functions, so this was for the low pass filter, the characteristic equation for the low pass filter is same as the characteristic equation for the high pass filter, which is also same as the characteristic impedance of the band pass filter. If they are same, then let us rewrite, suppose I write the high pass transfer function like this. So, we have okay. This I can also write it in a different way as VHP omega 0 square plus VHP S omega 0 q VI A2 S square. Now, if I divide both sides by S square, then what I will have is VHP plus 1 upon q omega 0 upon S equal to A2 times Vi square. Now, suppose we write a signal flow graph diagram. A signal flow graph diagram is a diagram which shows the various voltages as they are processed. So, instead of trying to explain what a signal flow graph diagram is, let me draw it. So, after this block diagram gives me the total picture of this equation. Look here, see what I have is this VHP. Okay. Can I write VHP like this as the summation of A2 Vi square minus 1 upon q omega 0 s minus omega 0 square s square V h p. Suppose I write that same equation like this, then you see that V h p is the summation of three quantities a 2 V I square minus 1 upon q omega 0 s and minus omega 0 upon square upon s square V h p. I should have a V h p, sorry, I forgot that. So, there should be a V h p here, sorry. So, you see that V h p itself is a sum of another two terms which are dependent on V h p. So, it is like a recursive. To get the current value of V h p, I have to use the past values of V h p to arrive at them, and that is what I am implementing here actually. See here, this is a summation, okay, of V I multiplied by A 2, okay. There is no square, I beg your pardon, there is no square in this term, sorry. Just note this correction, I had mistakenly put a square atop this V I square, V I, making it V I square. There is no square in the term V I. So, this V h p is equal to the summation of these two terms. So, what I did was, suppose I have the signal V I here, I multiply with A 2 and then add it to this summer. The other inputs to this summer are this omega 0 s square upon V h p. Now, the output of this summer is the signal V h p. Okay. So, this is V h p, this is also V h p. This is being first multiplied by minus omega 0 s. If I multiply it by minus omega 0 s, then scale it by 1 upon q, then this is this signal, this quantity. So, this is minus omega 0 upon s V h p. If I pass this signal through this block, it will be again multiplied by minus omega 0 upon s. So, at the output here we will get omega 0 upon s square times V h p. This I then scale by minus 1 and then feed it to the summer. Okay. So, then I get back, so this summer itself now generates V h p. So, this is what is known as a recursive filter. Okay. An implementation of this recursive filter would be something like this. So, this was the signal flow graph diagram. Just I want to repeat. So, signal flow graph diagram is a frequency domain. It shows the frequency domain flow of signal and the relation between the quantities and with the input signal. So, here this is when I say minus omega 0 upon h V h p, this is actually proportional to the band pass signal, and then this one which is omega 0 upon s square V h p, this is actually the low pass signal, proportional, not exact but proportional, because the exact signal, the exact signal has to be scaled with the appropriate gain values. A possible implementation of this circuit is using op amps, could be like this. So, we just follow the signal trail, how the signals are added, and by following them properly we will get our circuit. So, this circuit is this signal flow graph is implemented by the following circuit. So, this is my circuit. These are the various points at which I obtain my high pass, band pass and low pass signals, and the output equation that we get if we follow the op-amp analysis will be something like this. So, this V high pass will be equal to R3 upon R2 plus R3 1 plus RF upon R1 Vi plus R2 upon 2 plus R3 okay. So, this is of the same form as VHP minus okay. Now, here this gain from these capacitor based op-amps where the capacitors are connected in the feedback loop is minus 1 upon CSR, and this is equal to omega 0 upon S. So, then omega 0 is equal to 1 upon RC. Okay. So, the value of these omega zeros is 1 upon RC. So, this is of the exactly the same form that we discussed a few minutes ago here. So, this was the equation. This one represented the equation we obtained from the signal flow graph diagram, and this is the one we get from the actual circuit. Okay. Now, of course, to equate these two equations, the values of these R1, R2 and R3 should be such that RF upon R1 is equal to 1, R2 upon R2 plus R3 1 plus RF upon R1 is equal to 1 upon Q. Okay. So, from here what we get is that the Q value 2Q minus 1 should be equal to R3 upon R2. So, if we choose our RF, R1, R2 and R3 according to this equation, then we can implement this. Now, one circuit that I did not mention, which is frequently used for gain control in an active filter, is a what is called a buffer amplifier. So, we have already studied about buffer amplifiers while studying non-inverting op-amps. A simple buffer amplifier is like this. Okay. So, here VO is equal to 1 plus R2 upon R1 Vi, which is of kVi. So, for example, say when we take the output of these filters that I was mentioning, suppose let us consider this filter. If we want to take the outputs VHP, VBP and VLP and when want to scale it to the appropriate gain values, we simply can connect it to a buffer amplifier whose gain is controlled using this equation. So, this is nothing but this V I k plus k. So, in summary, in the past lectures we have covered a number of topics on active filter design, how to implement a filter using op amps for the first order case, and then for the second order case how to replace a passive inductor by an active implementation of an inductor. However, we saw that that active inductor so implemented can only be used for the band pass and high pass cases. And then finally, we saw a full implementation of low pass, band pass and high pass filters using what we call a recursive technique, and the same topology can give all the three types of filters. There are some more implementations of second order active filters such as the Sallen-Key filters, and which we have not covered. Now, one thing I would like to emphasize here, you saw that the difference between an implementation of a filter, of an active filter, between the first order and the second order is totally different. A second order implementation of a filter is much more involved than a first order implementation, and a third order implementation would be even more difficult. For passive case, it is not so difficult, all we have to do is add an extra ladder to increase the order of the filter, but for active filters it becomes very difficult. That is why whenever we want to implement an active filter, the order of the filter should be as low as possible, and therefore the prototype functions like the Butterworth or Chebyshev prototypes that we use, we should judiciously use them so as to keep the order of the filter to a minimum for the given specifications. Thank you.